transistor mode. Okay, no. Now, how you talked about, so you don't have those here, do you? All right, second, got to hand out notes first. Okay. There we go. So, okay, here we go. Now, for those of you who are in the subject for the first time, today's big idea is that there are different types of extrema. There's relative extrema, which is what we've talked about so far. In many books, that's also called local extrema. So relative and local extrema, we've done before. There's also the idea today, absolute extrema. In some books, you'll hear absolute extrema referred to as global extrema. Okay? All right. Now, let's talk about the difference between the two. Picture is worth 1,000 words. So look at this graph here. Now, you've got a lot of interesting points here. That point at A, it is the absolute minimum because there is no y value lower than that ever. This is a relative max. Now, it's a relative max or local max because in its little neighborhood, it's the tough guy. Okay, it's the biggest, the greatest in its little neighborhood. But in terms of the whole world, or globally, it's not the toughest or the biggest in the whole world. There is a point that's greater over here. So it's a relative maximum, but not an absolute maximum. Are you with me? Pretty straightforward. That's an inflection point. It's slow, but that doesn't have to do with the extrema. Let's go down to this guy. Point C is a relative min because it's lower than other points in its area. But it's not the absolute min because there's a point that's lower, right? Again, I'll remind you, local and relative are interchangeable. That guy D is both a relative max because it's the toughest in its little area, but it's also the global or absolute maximum because it is the greatest y value of all time. And then E is a local max, or min rather, because it's the lowest in its little area. By the way, this we could also say is a local min too. It's not just a relative. So I guess you could start by saying that absolute mins are less than all other y values or equal to, and absolute maxes are greater than or equal to. And they can also be relative mins because if they're greater than the whole world, they're also greater than their little neighborhood. Yeah? Pretty straightforward definition of absolute extrema is something like this. F at C is the absolute max of the function if that y value, f at C, is greater than or equal to all other y values. And obviously, by the same thought process, absolute f at let's call it f at D, is an absolute min if f at D is less than or equal to all other y values. You follow? Okay. Now then, sometimes you have an absolute min, sometimes you don't. So the next idea is, when do you have an absolute min? When don't you? When are you guaranteed to have it? Now, would you denote a few things? Wouldn't you agree that this is continuous? But it does not have any endpoints over an open interval. That first one. Now that is to say that it doesn't have endpoints. Okay, the interval goes from negative infinity to infinity, it's unbounded. Does this have an absolute max? Is there one y value that's greater than all others? No, it has no absolute max. Does it have an absolute min? Yeah, it does have an absolute min, right? There at the vertex, yeah? Okay, now my point is that by looking at a few characteristics, you'll see when does there have to be an absolute min and when could there be, but not necessarily have to be. This, I think you'll agree, it's continuous. But it is still an open interval. It doesn't have, I know it has an endpoint on one side, but it doesn't have an endpoint on both sides. So you would still call that an open interval, the fact that it's not finite. Does it have an absolute min? Does it have a y value that's lower than all other y values? Yes, it has an absolute min. Does it have an absolute max? No absolute max. Okay, cool. What about graph 3? Is it continuous? It is continuous. Is it an open or a closed interval? Does it have endpoints on both sides? Nope. Open interval. Does it have an absolute min or max? So I would just say no absolute extrema. All right. Part graph 4. Is it continuous? It is. Don't worry about the open circle. That's not a break in continuity. If that open circle were inside the graph, well then, yeah, we'd have a continuity problem. But that open circle just means that it's still an open interval. It does not have included endpoints. If it included that endpoint, then I'd have a closed interval. There are, is there a relative min? Yeah. Okay. What about a relative max? There's the relative min. The relative max, yes or no? Yes. Okay, what is the relative max? It's not that open circle because that's not included. So what is it? The point right before that? Okay. Too much of my question is obviously what the freaking heck are you talking about? What does that mean, the point right before that? What? What does that mean? Is there a point right before that? Yeah, no. There is no such thing as that. Okay. How many points in this area? How many points just in that little area? Infinitely many. So what's the one right before it? Trillionth away? Well, isn't there a point of trillionth away? Well, okay, what's then less than a trillion? Quadrillion. Okay, so forget within that, obviously there's infinitely many points there. What about in that? Infinitely many points. So there is no maximum because there is no such thing as the one right before it. That's not a thing. Okay? So there's no, oh sorry, that should have been relative. Absolute, there is an absolute min, but there is no absolute max because it doesn't include that endpoint, and there's no such thing as the point right before it. All right, last but not least, this, is it continuous? It is not continuous. Is it on a closed interval or an open interval? Closed interval. Does it have absolute min and max? Yes or no? No. No absolute min. What about absolute max? No. Goes forever up. No absolute max. Okay. Now then, it seems like if I don't have endpoints, then it could go forever, and that seems to be a problem. So open intervals seem to be a problem. Also, even when I have endpoints, if it's not continuous, I seem to have a problem. So then the point is this. What about if you were to graph a continuous function on a closed interval? And closed interval, again, I'll remind you, is the endpoints are included. Okay? Put your pencil anywhere. Put a dot there. And do whatever shape you want. There you go. Never lifting your pencil until you get to another endpoint. Does it have an absolute max? Does it? Is there a y value that's greater than or equal to all other y values? Yes, absolutely, 100%. Does it have an absolute min? Absolutely, okay? So the point is this then. That's the first part of the extreme value theorem. If a function is continuous on a closed interval, it's absolutely 100% guaranteed to have an absolute min and a max. It must have a min and a max. Now that's not to say that if it doesn't meet those conditions, if it's not continuous, it could still have a, for example, if I looked at this, this has an absolute min, just doesn't have an absolute max, okay? And if it's not a closed interval, or if it's not a closed interval, it can still have an absolute min or max. The idea is that if it's continuous on closed, it's guaranteed to have a min and a max. So, last thing here. If you look at this graph, at what x does the absolute max occur? At what x value is the absolute maximum? X equal c. At what is the absolute min? X equal what? F. Okay. Now then, if you were to look at that, if you look at where the absolute extrema could be, it has to have something going for it. The only place an absolute extrema could be is either at some kind of magical relative extrema, like where the derivative is 0, or the derivative is undefined. Isn't that a sharp turn there? So that's a derivative being equal. Or a derivative equals 0. Okay? Those are candidates for absolute min and max inside extrema. But I also have the possibility of ending at a point. And so these endpoints, they're also places where the absolute extrema can happen. But the good news is that that is the only two places, or those are the only two places where you can have an absolute extrema. If you look for an absolute min and a max, you only have to look one of two places. It's either an endpoint or a critical point. That's it. It can't be something else. You know, there's nothing special about this point. It cannot be absolute min or max. It's got nothing going for it. So to win the contest of the absolute min or max, it's got to start with being a candidate, either a critical number or an endpoint. That then leads you to the main type of problem. Okay? This will be worded a little differently, and you'll have to read carefully. It says find the absolute min and max, and that compares to find the min of f equals x squared kind of thing. This, or relative min, darn it, that's more like a first derivative test question. That's the old style. And you'll still have to be able to do those, you know. Use the first derivative test to find where this cube has a minimum. That's relative minimum, because a cube doesn't have an absolute minimum or maximum. A cube goes forever. This, however, is saying, I've got this cube, but I'm only taking a chunk of it up to a certain point. Now, the minute they stop it, it has to have an absolute highest point and an absolute lowest point. What are they? So this, that presence of absolute min and max, that's a totally different approach. You're not going to do the first derivative case. You're going to do a little different approach, and this is what it looks like. For those of you who are from Miss Cannon, I require this a little different, so I expect you to have these steps, all right? The first thing I was always taught to do is, if you're doing an absolute extrema problem, you start with the EBT, or the extreme value theorem. In other words, it's like the thesis of your proof. You would say, absolute extrema are only at endpoints or critical numbers. Telling the reader, you know what, there's only two different types of places it could be. So that's why I'm only going to look in these places, all right? Now the endpoints, obviously, they'll be given. The critical numbers, you'll then have to say, all right, here I go now. Let me find those critical numbers, those places where the derivative is 0. So the graph goes flat. It could be max's or min's there. Find the critical numbers. So wouldn't you agree we find critical numbers by finding where the derivative is 0 or undefined? The derivative is 3x squared minus 3. That is 0 at x equal. I guess I could do the algebra factor out to 3, but can you just tell me what are the critical numbers? Plus or minus 1, right? Does that make sense that a cube would have two critical numbers?
Yes.
Yeah. All right. Now, just so we're clear then, I've got two critical numbers. Now it really goes to, all right, where are those endpoints? If those endpoints were here, well, then they'll probably be the absolute min and max. But if the endpoints are more like here, well, then that relative one value might be the absolute min. So it really goes to, at those four possibilities, the endpoints and the critical numbers, what could possibly, or what has the greatest and least y value, right? So we need to investigate at the candidates, what is f at each of the critical numbers and the endpoints. Let's start with f at -2, or the far left region. What is f at -2? Now I'm not talking f prime at -2, I'm talking f. What's the y value on the original curve at -2? I get -1. Do you agree? Okay. I'm just going left to right in all my candidates. So my candidates are the endpoints 0, -2, 1, and -1. Now we'll talk about 1 in a second. But the next point I come to, left to right, is -1, right? If you put in -1, what do you get? I get 3. Okay. Cool. So in terms of the starting value, is it at -2, the y value is -1. By the time I got to -1, the curve had climbed to 3. Now I'm going to say what happens as we go to the next point. What's the next point of interest? 0, right? What's f at 0? 1. Okay? At that point, though, they're stopping it. They're not going to the next critical number. Yeah, 1 was a critical number, but is 1 in the interval? No, they're closing it first. No, positive 1 is not in the interval. So normally I would continue on and look at what's going on at that next critical point, but they stopped the curve right there, and we didn't actually get that fourth point as a candidate. Are you with me? All right. That's the evidence we're going to make our conclusion from. Our thesis is the absolute max can only be at an endpoint or a critical number. The greatest of the candidates was 3. And so we would conclude that the absolute max is 3 because now this is where you could say this one of two ways. Depending on your teacher, there's commonly two ways to say this. One is to say because it is the greatest of the candidates. And you say it in words. That's pretty common on the AP rubric, you'll see that written. Another is to say that in math, because 3 is greater than the other two candidates. Now those really say the same thing. The candidates for absolute max are these y values, and 3 is the greatest of those y values. They're both fine, either one's fine, whichever you prefer. So, what about the absolute min conclusion? The absolute min is -1 because it's either the least of the candidates or because -1 is less than all other candidates. Either one's fine. With me? Okay. So you state what you're going to find and where you're going to look. You find the critical numbers because those are interior min and max candidates. You find the y values at each possibility, and then you conclude based on the evidence. Let's try another one. Okay? By the way, I'm giving you the 4 steps here, reminding you as we learn. But I'm not basically within a day or two in the homework. It's just going to be a blank space, and you're going to have to know to do those 4 steps, okay? Slightly different, but very common. People enter at a rate of blah, 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 where time is hours since the store opened at 10 a.m. People leave at a rate of that parabola. There are 2 people in the store at 10. What is the maximum number of people in the store? From 10 to 4. Now notice, there is nowhere in the question it says the absolute maximum. This is where you have to read carefully. They say the max, not a max, not a relative max, not a local max, the max, the greatest. That is implied absolute max. And that's the hard part for students. You have to decide, is this a local max kind of question, or is it the absolute greatest value? And you have to read very carefully. It's very subtle, all right? So you would start by saying the absolute max is only at a critical number or an endpoint. That's the only place the maximum number of people could be. So thankfully, I don't have to look at the whole graph. I don't have to look at every point in the world. I just have to get a few possibilities and decide which one is the greatest. All right? Now, the endpoints, obviously, are given. 10 to 4. What are those in terms of time? Is that time 10 and time 4? Or do we have to tweak those a little? Tweak them. What are the endpoints? Time is hours since the store opened. So 10 a.m. is time 0, and 4 p.m. is time 6. Okay. You do have to do a little bit of thinking here. All right. The critical numbers, those are definitely the hardest part. The critical numbers generally are where the derivative equals 0 or undefined, right? The problem is this isn't a straight up theory problem. It's more of an application problem, and you have to do some thinking. So this is the thought process. Well, the derivative is a rate of change, yeah? And so if I want to know where the derivative is 0, I really want to know typically where the rate of change is 0. Where does it stop increasing and start decreasing, or something like that. In this case, what's the total rate of change? The rate at which people change, the number of people changes depends on 2 things. What? Enter and leave. So the total rate of change is really the combination of the enter rate minus the leave rate. You could also say that I want to focus on when the enter rate equals the leave rate. These both are the same. They're going to have the same solutions. At those instances where the enter rate and leave rate are the same, then the number of people isn't changing at all at those instances, which would mean before and after it is changing, it's growing or shrinking. So it's to focus on where those happen. That's logical because that's going to divide it up into increasing, decreasing. I need to then find where 2t plus 3 equals 6t minus t squared. Now, if this were a calculator problem, those functions are often going to be messy and you use your calculator to find those intersection points. But because this, I made the problem so super clean, this I think you should be able to solve by straight up algebra. I'm getting t squared minus 4t plus 3 equals 0. So t minus 3, t minus 1 equals 0. So the two rates are equal at time 1 and 3. If they're only equal then they're not equal every other time, which means it's got to be growing or shrinking everywhere else. So our candidates, our possibilities, our candidates are the endpoints, time equals 0 and 6, and the critical numbers 1 and 3. Those are the only times we can hit an absolute maximum. And those are the only times that we need to find. This is a huge free response question because it's got so many calculus ideas. We've already used a ton. Now we have to do even more. If I want to know how many people at these, I'm going to have to do some calculus. Now, number of people at time 0, that's easy. How many people are there at time 0? Who's kidding? There are 2 people in the store at time 0. So I know that it started with 2 people. However, every other amount, I got to go find. Now, if I want the number of people, and by the way, it represents the number of people at time t, to find the number of people at time, let's go to time 1 next, okay, because that's the next candidate in order. How would you find, how do we find the number of people in the store, given that we're given rates at which people enter and leave, not number of people who have entered and left, rates of change. How do I find a number given a rate of change? Integral, exactly. I need to take start plus add minus left, right? So let's start with how many started there. Then I'll add in how many entered and subtract away how many leave. Now I know the number to start with is 2. And to talk about how many enter and leave, I need to integrate from 0 to up to the time we're interested in, which is 1, enter minus leave. Now that's 2t plus 3 minus 6t minus t squared. Now I could find those separately and get a total enter and a total leave, or I could just do a net enter rate, enter leave rate, and integrate once. If you were to do that, I guess I'm going to need you to throw that in your calculator. Please, would you real quick throw it in your calculator. I guess we could integrate it by hand just as well. By the way, you could definitely combine the t's to the firsts if you wanted to. And if I were integrating this by hand, I absolutely would. Okay, so 2 plus shift plus 0 to 1. What is it? 2t plus 3. Darn it. minus, what's the new rate? 6t minus t squared. Did you get 1.333? Yes? Okay, that would probably imply that more people were leaving than coming because the number reduced. 1.333 or one person at time 1. What's my next candidate? Number of people, there's 0, 6, 1, and 3. So my next candidate is 3, right? That would be 2 plus the change from 0 to 3 of the enter rate minus the leave rate. So if you just go back and recall that previous problem, or not. Why is this frozen? Oh, it's because I have my pen in my... I get freaking lying. Come on, baby. Sorry. What did you get when you change it to 3? Geez Louise. Just tell me what you got when you went to 3, please. Somebody. We move on. Somebody. Change your upper limit to 3 so we can try actively engaging in your own freaking education. And we'll move on. All right? How do I get negative 1.67? Oh. Okay, what'd you get when you went to 0 to 3? 2. 2. Perfect. Okay, are they going exactly 2? Okay, 2. All right, the last candidate is number at 6. That's 2 plus the integral from 0 to 6 of enter minus leave. And what is that equal to? Change it to 6. $20. Okay, cool. All right, so our conclusion then is the absolute max number of people in the store is 20. And again, you could say or justify it one of 2 ways, because 20 is the greatest of the candidates, or because 20 is greater than the other possibilities of 2 and 1. All right? It can only be an endpoint or a critical number. The greatest of those candidates was 20. That's got to be the absolute max. It cannot be anything else. All right. Let's try throwing this idea on top of the fundamental theorem geometry problems. I've been trying to selectively choose problems like this that didn't have the absolute max idea in it, and that's not easy because most of these do have an absolute max component to it. So if you're given this kind of case, given the graph of f, and that G is the area under f from 0 up to a point, find the x where the min value of G occurs. That's the min, not a min, the absolute min. There's a big difference between the and a. Could be any local min. The min is the absolute min. The absolute min is only at an endpoint or a critical number. That's definitely one of the big ideas of the day. An absolute extremum, min or max, can only be at an endpoint or a critical number. The critical numbers are where G prime. Now here's where we make that connection to F. G prime would be the same as F is 0 or undefined. So what are our critical numbers here? Let's pretend this ends at, I'm going to put a dot there in case I don't want to get into what's on the far left side. So technically negative 3 is 1, but that's also an endpoint, so I could include negative 3 if you like. Where else? Or at, what else is F equal to 0? 1.5. Cool. Okay? After we decide, all right, the absolute min can only be at these places, and that's the endpoints of -3 or 3, or the critical number of 3/2. Now I need to actually find G at each critical number. Let's start with G of -3, the left endpoint. G of -3 means an integral from 0 to -3 of f. By definition, that's what it says G is all about. Anytime I have switch limits of integration, I freak out and say, oh, I can't have that. I've got to change them so they're going the proper way. When you switch limits of integration so they go the proper way, less to greater, then you negate, yeah? Afterwards, you finally do the signed area. Is that area from -3 to 0 above or below the axis? Above, and the geometry is pi r squared over 4 for a quarter of a circle. So altogether, G at -3 is -9 pi over 4. Cool. My next candidate is G at 1.5 or 3/2. That means what is the area accumulated from 0 to 3/2? This time I don't have to switch the limits of integration because they're cool. 0 to 3/2 is getting bigger. So I just talk about signed area. That area is a triangle. Base times height divided by 2. What's the base? 1.5. What's the height? Divided by 2, that's 9/4. The last candidate is the last endpoint, which is G at 3. 0 to 3, the curve area under 0 to 3, well, that's the area from here and here. And what do you notice about those areas? It's 0. They cancel each other out, so that's 0. The only 3 candidates for absolute min are these 3. Any other value cannot be the lowest, so I need to just choose between those. What's the absolute min value? Yeah. Okay. This is the last thing that I want you to read carefully. Okay. So would I be good to say the absolute min is -9 pi over 4? Just lost AP point because you didn't read the question carefully. All right. Often the question says, what is the absolute min value of f? But that's not what this says. It says, find the x where the min value occurs. And so your answer should not be -9 pi over 4. It should be the absolute min is at x equal -3. And that's one of those gotchas in there. You've got to read carefully. Sometimes they say, what is the absolute min value of the function? In which case you get the f value. But sometimes they say, where is the absolute min value? And you get the x value. So you got to read very carefully. You follow? Okay. Last but not least, would you throw those true or false questions down? Now let's see how they go. True or false on each of those. All right. Okay. Let's see. Larissa. First one, true or false? True. That is true. If f of c is greater than or other equal to all other f values, then it must be absolute max. That's the definition of an absolute max. That's 100% true. Kira, if f at c is the minimum, x equals c must be an endpoint or a critical number. That is true. The absolute min can only occur at an endpoint or a critical number. It must have something going for it. And last but not least, if f has no critical points, it has no max and min value. True or false? false. Give me an example of a graph that has no critical points but has them in a max. Actually, I'll just give one. How about that? That has no critical points, but that has an absolute minute max, right? So that is false. Okay, good stuff. That's good. Should we go over homework questions or test
The
based?
test. No, because I just saw.
I'm actually gonna.